So for this, we want to verify that 1 over 1 plus sine plus 1 over 1 minus sine is equal to 2 plus 2 tangent squared. Okay. First things first, neither of those sides look great. They both look like they're going to take work. And whichever one we want to start with doesn't make a great big deal of difference, but we've started with the left side on our other two examples. Maybe it'll help if we start on the left side again. Okay, so we've got two rational things, and much like that second example, much like that last example, generally we have rational things. We like sticking them together and hoping that the tree shakes into nicer places. So we multiply the first term by 1 minus sine over 1 minus sine, and the second term by 1 plus sine over 1 plus sine, so that on the bottom we have 1 minus sine times 1 plus sine as that common denominator, and on the top we'll get 1 minus sine plus 1 plus sine. And hey, a bunch of stuff cancels. On top, the signs will go away, and on the bottom, that term is what's called a difference of squares. So we'll be left with 2 on top, because we have 1 plus 1, and then 1 minus sine squared. The nice thing about 1 minus sine squared is it's a non-obvious but present way of writing the Pythagorean identity yet again. It's a very important one to know. So we end up with 2 over cosine squared, which, if you're clever, actually is all that you need, because, well, technically speaking, one way you could see the end here is that 2 over cosine squared is equal to 2 times secant squared, and 2 times secant squared is equal to 2 times 1 plus tangent squared. So, technically, you don't need to go both ways here, because you're actually pretty close to the end. It's just, well, it's a little bit subtle to get there. So, to get the idea, we'll see that you could adjust this from the other side as well to end up in the same way. So, assuming we don't make that connection that I just mentioned, you would then think about what you can do to the other side, where we have 2 plus 2 tangent, and that's not super useful by itself. But you can turn that tangent into a sine over cosine, so you get 2 plus 2 sine squared over cosine squared. And then, thinking rationally, you can try and stick those terms together using a common denominator of cosine squared over cosine squared. And you'd get 2 times cosine squared plus sine squared over cosine squared. And hey, cosine squared plus sine squared. There's a different Pythagorean identity. We've seen a couple times. That's just 1. So you get 2 over cosine squared, which is actually where we're supposed to end up. So, the thing with these problems is they're a lot like the eliminations we did in Chapter 8. Not in the sense that the math is very similar, but more in the sense that the approach, the central logic of having to push and pull, and maybe not always go in the exact same straight line from A to B, is the best way. And sometimes you have to wiggle your way around and push terms in directions that don't seem obvious. And maybe if you go from one side, get about halfway, and then pull the other side in to get it done. And this stuff might feel a bit motivationless, but it is actually very important, not just because it builds your understanding of how those identities work, how we can use them, but also because this is more a flavor of what real math is like, as it were. That there's a lot more things of ambiguity and uses of logic once you get into the real meat, once you get into the real ideas of what we're doing. This is probably a bit different than what you're used to, but I think it's really interesting stuff. Anyway, this is just a sense of what we're going to see with these types of identifications. Our next section is going to be continuing to build this stuff along, looking at a couple of important sets of formulas, these sum and difference formulas.